Okay, so we did the quartz method, or the quartz calculation. So now we have feldspar, olivine, and pyroxene. So now when you look these up, one of the things that's a little bit annoying is feldspar is a group of stones, right? It's not just one type. So you have to choose, okay, I'm just going to take a representative feldspar. So you can take, for instance, plagioclase or, something like that. And so then you look up its formula. So let's just look up the formula for, let's say, plagioclase, feldspar. So looking up the formula. Excellent. That's not. Webmineral.com. Here it tells you the answer, 270.7, and gives you the chemical formula down here. So I'm going to go ahead and copy the formula because my whole point is showing how to do this. So I copy this formula.
Yikes. So what if we don't use that same formula then?
You're going to get a different percentage, but I believe your answer will still be the same. That is, it'll still be in the same order. That is good to know. Thank you. Once again, you're not supposed to be using your cell phones during class, right?
It came through my watch.
Came through your watch.
If you were using the desktop, a message would have popped up on that.
Mm-hmm.
Why is there not an alarm or
Yeah,
something
like, why would we sound off?
on the phones?
I think the moral of the story is we should always be on our phones and be conscious of what's going on.
Yeah.
I will pass that on to administration. The students came up with the conclusion that they should be using their phones during class. It's the only way to be safe.
It actually came through my watch, so I wasn't using my phone, so that's a false statement.
Yeah.
I like alarms. I just don't like why they like scare you or something.
My watch buzzed, but I was in class. I'm not checking those things, right?
Sometimes you do.
When it talks to me when it's not supposed to.
You have a question?
Yeah.
How did you get,
Are you raising him like this?
because I'm stretching at the same time? Why are you judging her?
I was asking. A question.
Okay, let's get to the question because we're losing precious time.
So I'm wondering how you got the 47% out of the 20.
Well, I got it from memory, so let me actually put the numbers in because it's 28 over 60.
Oh, 28 over 60.
Yeah, it is 47. So now I put 28 over 60 in the calculator. It's more accurate than memory. Okay, so this is funny because it shows Na.5, Ca.5. What do you suppose that means?
Half of the molecule.
Yeah, you have sodium or calcium that are interchanged in the structure. So what we do is we say, well, the mass of silicon in this, how many atoms of silicon do I have in a molecule of this plagioclase?
5.
It's the subscript, which I know you can't see the subscript from the copy paste, but 3 was the subscript. So it's 3 times the 28 atomic mass units. So 3 times 28 is 84. Is that right? So 84 atomic mass units are silicon. What?
So you have the calculator right next to you.
Yeah, but we don't use calculators for simple math. We use them for hard math.
False statement.
Tell that to the people who
Yeah,
enter 2 plus 2 into the calculator.
False statement.
I'm sorry. Now for the mass of the plagioclase.
So is this B?
Yeah, this is B.
This is confusing.
So we have 0.5 times the mass of sodium. What's the mass of sodium?
It is 23.
Okay, so we're just rounding to 23 plus 0.5 times the mass of calcium. What's the mass of calcium?
40.
Plus, and then we have, of course, the 3 times the mass of silicon plus aluminum 1 aluminum. So 1 times the mass of aluminum. What's the mass of Al? I believe it's the one under B.
Oh, 27.
27?
Yeah.
And then finally, plus 8 times the mass of oxygen, which is 16. Now, you understand I got the 8 from the subscript on oxygen, the 1 because there is no subscript on aluminum, the 3 from the subscript on silicon, and so on, right? Want to make sure it's clear to everyone where we got these. So if we add these all up, we have, well, 23 plus 40 is 63 divided by 2 is 31 and a half plus 84. Okay, I'm not going to do it all in my head.
Yes, please do it on a calculator.
Plus 8 times 16. So that's 270.5 U. And so then what percentage is silicon?
84 divided by 2. Yeah,
And so that gives us 31%. Now, in my answer key, I used a different version of feldspar. I used potassium feldspar, so I have a slightly different percentage, but I think they'll still fall in the same range. That is, this one's above this one. And so you do that. Now we've done it for 2 of the 4. So do the other 2, and then you just rank them from which percentage silicon will freeze first.
Yeah.
High or low?
Oh. All of them first.
Okay, high or low percentage of silicon?
It's low.
Okay, low percentage of silicon will freeze first. And so after you found the percentage of silicon in each one, then you just organize them from the lowest percentage to the highest percentage.
Okay, and then how do we get the, that for each of the small?
What is that? The chemical formula? Just look it up.
Okay.
You saw, I just Googled it.
So when we turn in our homework, can I put a piece of paper over this and take another picture?
Sure.
I do not want to rewrite these.
That's fine.
We did this
That is
very
fine.
wrong.
That is fine. Okay,
Okay, are we good?
moving on to newer material.
Do we have to have a PTQ?
Do we have to? Yes, we should have a PTQ on the next 20 minutes of lecture.
But there's only 20 minutes.
That's right. We'll have a PTQ on it.
That's not fair.
It's really not.
Thank you for letting us
It
make
is-
our own quiz questions. We really appreciate it.
Amber, you're not helping anything.
Okay. So, yeah, we've already talked about this section here, but the rock types, igneous, sedimentary, and metamorphic, is what I'm going to start with here, being careful with each one. So, igneous rock. What did you learn from Hannah about igneous rock? Go ahead,
They
Grace.
come from volcanoes generally, and they melted stuff.
Okay.
Yes.
Comes from melted rock. Igneous comes from melted rock. And what do we call melted rock below the surface of the earth? Magma. What do we call it above the surface of the earth?
Lava.
All right, you guys are totally down with that. So igneous rock, it was melted, then it freezes. Sedimentary rock is rock that was broken down into small pieces. And when we say small pieces, small is a relative term. And then it was compacted and cemented together to form a new rock. So the chemical composition of a sedimentary rock doesn't have to be consistent at all. You could have had some rock came from this source, some rock came from this source, and they then got compacted together to form sedimentary rock. Often it is consistent because often you have the same source for both. So sedimentary rock is small pieces that were compacted, so it doesn't involve melting.
For
If it was granite versus limestone, if you look up pictures of granite and limestone, limestone has more sharp edges, so it would be harder for limestone to be a sedimentary rock.
Well, limestone is,
This is
that limestone is a form of calcium carbonate that I believe is formed through sedimentation.
So then on the homework, when it asks about that, then granite wouldn't be more sedimentary.
Granite is igneous. Granite was melted and then solidified. Whereas the limestone was deposited chemicals. So they're fundamentally different. Finally, metamorphic. Metamorphic rock is rock from any type that has been heated or put under extreme pressure, or in some cases, fluids like water have caused it to be modified. And so that's where the difference is between marble and calcite or limestone or any of the other names for calcium carbonate. Marble is metamorphized. It's been heated and squished and deformed. So, okay, we already talked about that. Everyone knows that. I read an article yesterday that was really interesting, I thought. It was talking about what's going on inside the earth and that they're learning new things about what's going on down there. That somewhere approximately, I think it was 400 kilometers below our feet, we have the boundary between the upper and lower mantle. And at that boundary, they have enormous mountains. They have sharp, jagged peaks. Now, of course, what's above the mountains? Let's just say rock in a squishy form, right? It's probably correct, but it's also not purely melted.
Okay.
It's kind of in a quasi-liquid state. So they're finding more and more interesting stuff. That magma, the material in the mantle comes up, pushes the plates apart, like I talked about before, making the rift valleys. And then when it comes back down, it brings down pieces of crust. So the crust does get recycled into the mantle. And so there are big plates of rock that used to be part of the crust that are now down in the mantle because of that cycling. And so it's really something that is, our knowledge about it is evolving, is developing still as we go on. The role of heat. Temperature increases as you go down in the crust at an average of 30 degrees Celsius per kilometer. So now, something you may or may not know, if you live somewhere and it's really cold, something you can do to heat your house is to dig down 20, 30 feet, and the temperature is going to be a nice temperature. And so you can use that warm temperature to heat your house. Or if you live somewhere really hot, you can do the same thing. Dig down 20, 30 feet, I think it's all you really need to go. And you will have a nice temperature, and so you can use that to cool your house. So I have a friend who lives here in Lincoln, where they live in a community that actually does that. The community, each house has a setup where they down low to get the nice temperature, and then they have a lake where they use for cooling hot and for, I think probably for heating some cool as well. And they use that for heating and cooling their houses. So it is actually a eco-friendly way of heating and cooling. And once you get it built, a cheaper way. So here is the thing why I was not just saying magma with Bryson's statement. Rocks in the lower crust and upper mantle are near their melting points. So they're not really molten, but they're near. So they're in the stage where you can metamorphize. I actually want to keep going here because we have missed a lot of time. A lot of time. Okay, I'm skipping through things to get to what I want to cover. Okay, different classifications of igneous rocks. Basaltic is about half silica. What did we see that was half silica? Quartz was half silica. Basalt's about half silica, and about 80% of all igneous rocks in the crust are basalt. Has anyone seen basalt? Your ocean floors are largely basalt. So remember, 90% of all rocks are silicates. 80% of the igneous rocks are basalt. Now, igneous rocks are not all rocks, so that's not saying 80% of all rocks. Andesite is about 60% silica, so that's even higher silica concentration. Now, silica, I need to be careful. What we calculate was silicon percentage. Silica is SiO2, so that's, of course, is 100% silica. And granite is about 70% silica. Only about 10% of the Earth's rocks are granite. Something that is not mentioned here is the rate of freezing. Granite freezes very, very slowly, whereas basalt freezes very, very quickly. And so the granite is going to, because it freezes slowly, incorporate everything. The basalt, apparently not as much. Plutonic. Anyone heard of a pluton before?
Wait, can you go back really quick?
I can.
You gotta take a picture.
Anybody heard of a pluton?
It's like
The plutons are big chambers of magma that cool and freeze. They cool and freeze over a very long time. What kind of rock can you create if you have a big chamber of magma that cools and freezes over a very large time? It's going to be what?
Sedimentary? Metamorphic?
If it was molten, it's got to be igneous. But what kind of igneous rock freezes over a very large time? Granite. So you form a lot of granite in those. Now, rocks that form, so plutonic rocks, granite is a good example of a plutonic rock. Volcanic rocks are the ones that actually come from a volcano. We've been talking about volcanoes with igneous rocks, but those are the ones that form at the surface. And you have things like your, well, tuff is an example of a granitic, volcanic. I got granite in my head now. Of a volcanic rock. Tuff is ash that has compacted to form a rock. Ash means essentially the silty rock that is broken up when it blows up. So we have different kinds of volcanoes. Has anybody been to an active volcano?
Yes.
You have? Awesome. Where? Chile? I've never been to one myself, so that is awesome. There are different kinds of volcanoes. Now, I've been to former volcanoes, to ones that are dormant. Depending on who you talk to, there is no such thing as a former volcano. They all potentially could erupt again. But of these volcanoes, you have different types. The one on the left there, you look at the shape and it's pretty smooth. It's called a shield volcano because it's shaped kind of like Captain America's mighty shield. So shield volcanoes have a shape like a shield. A cinder cone volcano is the kind of volcano that you typically see pictures. The cinder cone has the sharp edges, and when it blows, stuff blows like this and builds it taller and narrower. This one here is marked as composite. When I look at that, I would have thought that looked like a cinder, but I guess it's just not steep enough to be a cinder cone. And so it's a composite. Now, one thing that instantly comes to my mind when I see there's different types of volcanoes is to question why. Why would I have some volcanoes that form a shield shape and some that form this big cinder cone? Do you have any hypotheses? Right, remember, scientific method, you know something interesting, the next step is develop a hypothesis that explains why it occurs is based on scientific ideas and makes testable predictions. So why do you suspect that you would have shield type or cinder cone? Yes.
I have a question.
Yes.
So in Panama, we stayed in like a dormant one.
Mm-hmm.
Like there was a hotel in the middle of it, but like I feel like what could that have been on this list?
Not having seen it, I couldn't tell you which one it was.
Because like it couldn't be a composite one. Like what?
Well, the composite is not a sharp cone, not a pretty flat shield.
I feel like it would have to be the flat one.
Yeah, I didn't see it, so I have no answer. Right, you have to actually see it to know which type it is.
I think
But go ahead.
the composite, the magma or lava flowing out the top cool, and it formed that shape maybe. And then with the solar bear cone, maybe it was just all blown out in a more violent eruption.
Okay, so Bryson says, now I'm just going to go shield versus cinder, right? Composite is between. So the shield cone, it flows out and solidifies, whereas the cinder cone, it's a violent eruption. So that's a hypothesis. How is that backed up by scientific ideas? I mean, I'll help you out by saying that is the hypothesis, that's the theory. Okay, go ahead.
I mean, you can hypothesize that by looking at past eruptions.
Okay, past eruptions. Well, I would go with something like, well, if you have a violent explosion, stuff is going to go up everywhere, and if stuff goes out in a spherical shape, you're going to have a lot of stuff that goes a lot straight up and comes a lot straight down, smaller amounts that go out comparatively, and so you expect it to build up more toward the center. Whereas with flows, we see flows all the time. You pour honey on your cereal, and initially it might be tall in the center, but then it's going to flow out and form a pretty flat thing. And so that is what we understand to be the difference. The shield volcanoes, the magma comes out and it flows. So it's a kind of magma that flows easily.
But then in the cinder cone, they're more violent than the shield.
In the cinder cone, the magma doesn't flow. So what it does is it basically forms a dam, because it doesn't flow until you have high enough pressure to break that dam, and then you have a very violent eruption. So that's the difference in the cinder cone versus the shield. Now, the Hawaiian Islands are volcanic islands. That's the place where most people who have seen a volcano have seen an active working volcano. What kind of volcanoes do they have there? Are they violent explosions or are they flowing?
They're probably both.
Okay, shield is correct. They're shield volcanoes. The magma, people can go out there and they can see the magma bubbling like this. Right, that's stuff that flows reasonably well. Huh?
I've seen videos of that.
Yeah, I've seen videos of that. And then the magma flows out to the ocean. You might remember just a year ago, there was a big lava flow that reshaped, I can't remember which island it is now, but reshaped one of the islands. It filled in a very popular tourist bay with magma. It just went flowing down the hill. And it's flowing at what, 5 miles an hour or something? It's not like it's going to catch you unless you take a siesta, but you can't stop it either. And so people's houses were completely taken out by the magma as it flowed down the hill toward the ocean. So the Hawaiian Islands are shield volcanoes formed by nice flowing magma. Now, something that's interesting, this is what we're going to actually do in the lab, is how the different types of volcanoes occur. So here is a basic picture of a volcano. You have a magma chamber with some pathways to the surface. And so this here is showing, well, here you have what looks like an eruption, but you have lava flows. So what kind of volcano is it going to be if you have lava flows? Shield, right. So this is a basic shield. And I don't remember, I'm going to talk about Yeah, I'm going to talk about the Hawaiian Islands here. I'm pretty sure it's late in the lecture. We only have 5 minutes. The Hawaiian Islands are created from one hot spot. Okay, I'm going to actually try to find the picture because I'm sure I have a picture of it. Not that picture. You can see I came prepared with pictures. No, I don't have a picture of it because that was the last one, the rock cycle. Okay, so the Hawaiian Islands, you have one hot spot. So you have this magma chamber and it punches through. So right there's the hot spot. But over time, we have this thing we call plate tectonics. We talked about that, the plates sliding over the surface, the lithospheric plates. And so as those plates move, here's the hot spot, and the plate is going like this. And so the plate has the hot spot under different parts. And periodically, that hot spot will punch through. And when it punches through, you have a new volcano. So all of those Hawaiian islands, Oahu, Hawaii, Lanai, Molokai, those are all the results of one single hotspot. And in fact, that hotspot is responsible for the islands going down to Tahiti and down by Australia. It's one continuous island chain that was produced by one hotspot, and the Earth's crust moved over that hotspot and punched up new islands. And so the newest island is still being formed. Actually, the newest island hasn't reached the surface of the ocean yet. It's still forming underwater. And so eventually there will be yet another Hawaiian island as that island grows, or as that volcano grows. And then you have older islands have eroded away and become smaller and smaller. You have erosion and weathering. Weathering, breaking the material apart. Erosion, transporting it away. And so that's how the older ones are getting smaller. So if you look at a picture of the Hawaiian island chain, you can actually see, it's moving this direction because I have the newest ones here and the oldest ones here, and they've all been formed over the same hot spot on the Earth. Okay, sedimentary rock. Hear those words: weathering, breaking rock. What things did we talk about during our walk that would break the rock?
Isn't it like walking on a path?
Okay, mechanical weathering is the term we use for that. You walk on it, you break it apart. You can also have chemical weathering. Things like if I put acid on a limestone rock, it will be chemically weathered. Or water running over any rock will chemically weather it over time. Then we have erosion. Erosion is actually moving it. And obviously water is a major carrier or a major conduit for erosion. Wind can also be a conduit, so can the motion of animals. Deposition, where it falls back and ends up. And then sedimentation is the process of forming rock. So these are the 4 steps, or 4 stages, I guess it says here. For sedimentation, you have your initial rock. It first has to be weathered, broken apart. Then it has to be transported, the erosion. Then it has to be deposited, and finally, the sedimentation occurs.
What is liquefaction?
That means making rock. Talked about those. I talked about this during our walk again, the frost wedging. The reason we have all the crazy potholes in this city is because water gets down in a crack, and then that water freezes, expands, and breaks the rock apart.
But they don't completely fill the potholes?
No, they don't. They do a horrible, horrible job of that. They were doing it out here in front of the school as I was driving in. You've got gravel with asphalt all over the road. You've got potholes that are semi-filled in.
I have a question.
Yes.
Actually, I did have a question on that. So, like, how you